Hello everyone, my name is Santosh. In this video we are going to discuss about intrinsic semiconductor and extrinsic semiconductor. Especially we will discuss about the n-type semiconductor. So intrinsic semiconductors are pure elements and having energy gap around 1 electron volt. At some temperature, non-zero temperature, or we provide some energy, then electron will excited from the valence band to the conduction band, leaving behind a hole inside the valence band. A empty space in the valence band is called hole. So their number will be same. When we give extra energy or temperature, then more electron and hole pair will generate. Number of electrons is equal to number of holes in the intrinsic semiconductors. So accordingly, first point, free electron density is equal to hole density. Density means number of free electrons per unit volume. It is called free electron density, represented by small n. Number of holes per unit volume, it is called hole density, represented by P, and both will be equal, and it is equal to Ni, which is intrinsic carrier concentration. So we can represent it Ni. And about their Fermi energy, the Fermi energy formula EF equal to EV plus EC by 2 plus 3 by 4 kBT log mH star divided by Me star. mH star is effective mass of hole and Me star is effective mass of the electron. At 0 Kelvin temperature, this term will vanish and Fermi energy is equal to EV plus EC divided by 2. EV equal to valence band maxima, EC is equal to conduction band minima. It is average of this, that is EV plus EC by 2, that is at the mid of the band gap. The Fermi energy will lie at the mid of the band gap at 0 Kelvin temperature. Third point, electrical conductivity, sigma equal to mobility multiplied by concentration multiplied by charge for electrons and for holes, and for intrinsic semiconductor n equal to P equal to Ni, you can take Ni outside. Ni E times mobility of electron plus mobility of hole. It is electrical conductivity of an intrinsic semiconductor. We should know about mobility, either electron mobility or hole mobility. It increases initially when temperature is less than Debye temperature, accordingly T raised power 3 by 2, and decreases further at high temperature, accordingly T raised power minus 3 by 2. And fourth point, n equal to P equal to Ni. If you multiply n into P, it is equal to Ni square. So Ni square is equal to n into P. Concentration of electron multiplied by hole concentration, and this law of mass action is also valid for extrinsic semiconductor. To make semiconductor either n type or p type, we have to dope intrinsic semiconductor with pentavalent or trivalent impurities. To make it p type, we have to dope trivalent impurities like boron, aluminum, gallium. To make it n type semiconductors, we have to dope it with pentavalent impurities like phosphorus, arsenic, antimony, etc. So n type semiconductor, which is doped with the pentavalent impurities, the doping concentration is very small, then it will not destroy the structure of the silicon. Its concentration is ppm, like 1 ppm, 10 ppm, etc. part per million, 10 to power 6 atoms, and impurity is then 1 or 2. So in case of phosphorus doped in the silicon, it replaces a silicon center or atom, and 4 electron of phosphorus make bonding, covalent bonding with the surrounding silicon, and 1 extra electron, that extra electron is loosely bound with the P, and it has little bit higher energy, then its energy will be just go beyond, like it will lie below the conduction band. Due to the loosely bound, it has higher energy in respect to other bonded electrons, so it will just lie below the conduction band minima, and this gap is very small, around 0.05 electron volt, so it can easily ionized. Here enormous number of free states, and electron can excited to the conduction band, leaving behind the immobile ions. These ions are these atoms at the lattice point, and it is stable, that is not moving. That's why just it is like a ion here, and electron go inside the conduction band, which is treated as the free electrons, and it is treated as the immobile ions, not holes. Do not be confused about holes and immobile ions. When electron go from valence band to conduction band, in that case the empty space in the valence band, that is called hole. Here immobile ions and free electrons. So number of free electrons increases enormously. N is much greater than the P. first point. And number of electrons in general we can treat it is equal to ND, donor density. Number of donors per unit volume is called donor density. For calculation purpose, we can calculate P, whole concentration, from law of mass action N into P equal to Ni square. From here P equal to Ni square divided by N. Third point, electrical conductivity. Since whole number is very small, then we can easily neglect this or vanish this, and sigma equal to concentration multiplied by electrons mobility multiplied by charge. Now we will discuss about the Fermi level in N-type semiconductor. So at 0 Kelvin temperature, Fermi levels lies between donor level and conduction band minima. And if we increase the temperature, further increase the temperature, it will shift towards the center of the band gap. Why it is shifting towards the center of band gap? Because if we increase the temperature, at sufficient high temperature, large number of electrons will generate from the valence band. That makes electron hole pair. That is, if electron is going from the valence band to conduction band, then it will leave behind holes. The number of holes further increases, and the number of electrons, number of holes will generate in the same number. Initially at low temperature or around 0 Kelvin temperature, only free electron is generated and leaving behind the immobile ions. But at high temperature, hole is also generated. Then the Fermi level will shift towards the center. Fermi level, that represents occupation probability being 50%. So initially it is here, inside here, occupation probability 50% here, but number of holes, if more and more holes generated, then probability will lie decreases and it will lie at the center, around the center. So T increases, EF moves towards the middle of the forbidden gap. At sufficiently high temperature, intrinsic behavior will dominate. In this slide, we will discuss the concentration, free electron concentration. Initially, it is increases exponentially. This region is called ionization region, and at some temperature, all donors will be ionized, leaving behind the immobile ions. Electron go inside the conduction band. The number of free electrons will be constant. So this is the constant or saturation region. It is also called as extrinsic region. And further increasing the temperature, electron will generate from the valence band, also generating the holes. So this is called intrinsic region. So there are three regions. This graph is also valid for p-type semiconductor as well, which we will not discuss about the p-type semiconductor in this particular video, but you should know that the graph will be same. Both graphs are valid for n-type and p-type semiconductors. And if we discuss about the conductivity of n-type semiconductor, so here it is increases, and after that it will a small drop, that is conductivity will decrease on increasing the temperature due to mobility. In this region, mobility is proportional to T power minus 3 by 2. The mobility, due to decrease in mobility, conductivity is decreases, and further it will increases due to the large number of free electrons and hole in the intrinsic region. So in this video, we discussed the conductivity of n-type and intrinsic semiconductors and their behaviors. Okay, thank you.